So I'll be presenting the first half of the lecture, and then Bo-Lee will likely arrive, and then she'll present the second half. But the theme for today is speaking about benchmarks. How do we measure capabilities? How do we measure safety properties of models? So we'll look at multiple examples of different benchmarks in both capabilities and in safety. And I'll also have some general remarks on evaluations more broadly and how to think about safety as being something distinct from general capabilities. So at a high level, first I'll talk about the benchmarks and evals, then I'll talk about benchmarks for capabilities, and then benchmarks for propensities, and I'll cover some specific concrete benchmarks along the way. So first, with benchmarks and evals, here is from a recent workshop, a list of all the possible things you might want to evaluate or benchmark. Maybe you want to measure intelligence, and so we need to have a planning benchmark or a creativity benchmark. Perhaps the memory is very important to benchmark as well or evaluate. If we're looking at hazardous capabilities, you might want to look at its cyber offensive capabilities, or whether it knows things about chemical, biological, radiological, and nuclear weapons. That's that CBRN thing there. Maybe we want to evaluate how does the model impact society. So can it be used to accelerate AI progress? So anyway, there's a lot of words basically. When you're wanting to benchmark something, people will often have some sort of vague words about some desiderata, and then the real challenge is how do you actually concretize something like creativity or intelligence or factuality or planning. So it's easy to have a write down the word, but it's not just a matter of collecting a data set for it. It's often fairly difficult to concretize it. So one question is, how do we for example, if we're trying to measure general intelligence, we don't just say measure intelligence and collect some questions for it. There are various desiderata, or various things you need in constructing a benchmark for general intelligence. Maybe you want some property like superhuman scaling so that it doesn't saturate, so that it can, as the models get better and better, you can keep tracking the progress. You don't want it to quickly hit its ceiling. If it can go beyond average human level, that's maybe a useful thing to do. Maybe it can go beyond expert level at some tasks, for instance. Maybe it could get superhuman. So that might be a property you want to look for when you're trying to come up with a general capabilities benchmark. Another property is you might want automatic evaluatability. So that's because you want fast feedback loops. If you're going to have the AI generate a result and then some humans evaluate it, that will make your experimentation substantially slower and will deprive you of an empirical feedback loop. It will reduce reproducibility as well. The reason, if you're having humans in the feedback loop, is that a reason that creates a challenge is if you're in an academic context, you're going to need IRB approval for running some MTurk, Amazon Mechanical Turk experiments to get human feedback. And so that's going to take you, maybe it's going to make your PI go through Amazon or through IRB training, and then you're going to have to ask some bureaucratic machination for a credit card, and it's going to take them 2 months to deploy $2,000 to get some crowd workers. So anyways, this is why automatic evaluatability is quite important, and if your benchmark doesn't include it, it's probably not going to catch on. There's other things like ease of setting up. You might think, I'm going to have a video game benchmark. Okay, if you're requiring things like Windows as the operating system, and it requires some specific DirectX driver or what have you, this will just make it far too difficult for people to set up. So is it plug and play? Or does it require substantially more expertise or a very specific environment? If it requires a very specific environment, it's too cumbersome. Reproducibility, you might want it to be deterministic. You don't want it to depend on the day it's run. That way we can compare models across various different setups and times and years compared to the yardstick changing each day. So that's another important property. Further, you want an increase in the benchmark implies an increase in performance on downstream tasks, if this is a general capabilities benchmark, or you want if a method that increases the benchmark should give rise to something that could help with downstream performance. So you want to look at a correlation. Are you just measuring some property in a vacuum, or is it connected to things that you care about? You want the metric to be interpretable. If your metric is something like in bits or nats, like natural log units, that's not very, I don't know what the difference between 2.2 nats and 2.1 nats is. I don't really know how to interpret that, but an accuracy difference of 70% and 75%, okay, I know what that means. And then finally, this needs to be useful for hill climbing on. This shouldn't have sudden jumps. It needs to be nice and continuous. It needs to have progression. So it can't be an indicator function. It needs to be smooth. And what this means is it often needs to be a composition of a lot of different subtasks that you're measuring, and its competence on lots of different subtasks so that it can have some smooth, so that it'd be the sum of multiple different sigmoids. But if it's it can do it or it can't, that's not very useful for testing new methods on. That's not useful for iterative progress, because when you're developing methods, you're going to need to discern between methods that work slightly better than the existing methods. That's because progress is largely an accumulation of many incremental steps with some occasional step changes, but you'll deprive of any type of signal for quote-unquote graduate student descent if it's just a big step function. So anyway, so as we can see, there are all those words from before, creativity and dangerous capabilities and alignment. And if you're going to create a benchmark, you're probably going to want many of these properties, and this makes benchmark design often more of a combinatorial optimization problem, where you're needing to make various trade-offs between different qualitative desiderata. I'll speak about a benchmark, or some benchmarks for capabilities that I guess are fairly well used. I mean, I think maybe like the most downloaded capabilities benchmark on Hugging Face at least or so, which we did a few years ago. So it's called MMLU. Basically, MMLU, it has a lot of questions from a lot of different areas. So an example question is find all C in Z sub 3 such that that thing is a field. Or here's a professional law question. I'll actually read this question just so you can get a sense that these aren't doing stupid, we're not asking the LLM silly questions. Like it can be slightly challenging. So we have a seller, which is an encyclopedia salesman, approached the grounds on which Hermit's house was situated, and he saw a sign that said, "No salesman, trespassers will be prosecuted. Proceed at your own risk." Although seller had not been invited to enter, he ignored the sign and drove up to the driveway toward the house. As he rounded the curve, a powerful explosive charge buried in the driveway exploded, and seller was injured. Can seller recover damages from Hermit for his injuries? And there'd be yes, unless Hermit, when he planted the charge, intended only to deter, not harm intruders. Yes, if Hermit was responsible for the explosive charge under the driveway. C, no, because seller ignored the sign, which warned him against proceeding further. Or D, no, if Hermit reasonably feared that intruders would come down to harm him and his family. So maybe think for a moment, what's the answer to that? I mean, so the answer is B. But this is just if you've taken some basic law courses, then you'd be able to answer it though. But anyway, they've pre-trained on so much, and they're given for kind of complicated scenarios with lots of mitigating factors. And this is one of the harder things for models, even such as GPT-4. But if saying that it's multiple choice questions, how easy? If that's the case, then I should expect everybody to get perfect on all their exams during this semester, since I imagine many of your exams will be multiple choice. So many people do treat multiple choice as though it's somehow a strong limitation. I don't see that, and I don't see in practice people actually acting as though that's the case. Here are other examples. There's conceptual physics, college mathematics, and there's that same professional law question from before. But here's what the results looked like back in the day, back when we just had GPT-3, and there was few-shot performance. If you looked at the small version of GPT-3, the Ada, Babbage, Curie, and then extra large was Da Vinci. The random chance performance, since there are 4 questions, is 25% chance. And you can see that only the largest model was able to, in a few-shot way, start to answer these sorts of questions. But the smaller models just were not picking up knowledge. And then I also am showing common sense and linguistics benchmarks, because that's primarily what the field of natural language processing was focusing on. Before this benchmark, they're largely just focusing on syntax type of things and sentiment classification, these sorts of issues, as opposed to what's its knowledge about anything. Is this a potential search engine replacement? So here's what the numbers looked like back in the day. Around average performance, unified QA was a 11 billion parameter model, and GPT-4, or this is GPT-3, getting about 44% accuracy. Here's a blast from the past. Back when, this is what the scaling curves looked like back in the day with a unified QA model. You would scale transformer parameter size against accuracy. And from this, one could guess that maybe when we reach 100 trillion parameter model, we'll be getting 85% accuracy. Now, we don't need that many parameters these days because of chinchilla scaling laws, but this is sort of how a lot of this analysis was done just a few years ago. But as you could see, it looks like scale helps, and helps reliably, and indeed it did. So here we are with GPT-4 plus a code interpreter, and this is the per subject breakdown. So high school government and politics, that's an AP exam. High school computer science, that's AP computer science. High school psychology, AP computer science. So all the high school ones are AP exams, or most of them are largely AP exam style questions. There are other subjects such as, what's one I'd like to draw attention to? I guess we could look toward the end. There's professional law. It's the second to the last. Virology is worst, but that's that's not because virology is difficult. That's an artifact of somebody inside of OpenAI made it just pretend that it can't answer those specific questions. You can ask it other virology questions, and then it can answer them quite well. So it's like, I don't know if somebody had a mandate to, like, you need to reduce the virology performance so that it can't be used for like bioweapons or something, and then they just like made it like do worse on it. But you can give it other virology questions, it can answer it extremely well, just as biology, just as they can answer many biology questions. You could actually spend many minutes looking at this plot, for instance. Here's, if you notice, there's college biology and high school biology. Here are 2 red bars there. They're very similar accuracy. One is AP biology, and one is the GRE subject test for biology. The GRE subject test for biology is for admissions to PhD programs in biology. So it's 4 years more of extra experience required for it. Nonetheless, it's basically getting about the same level of accuracy. This is to say that what the LLMs find difficult is not necessarily what humans find difficult, and what they find easy is not necessarily what humans find easy. So they don't have it's not the same. They will sometimes do worse, or they will sometimes do better on like. If you don't give them the code interpreter or the calculator, they will do better on like college physics than they will on like 8th grade, on elementary mathematics. So like they can learn capabilities in a very unusual order. But generally, biology is an easier subject to learn. Professional law is one of the hardest. So are things like econometrics and college chemistry. College mathematics is the GRE subject test in mathematics. Where is college physics is? Wow, that's very high. Okay. Yes.
Does the model have access to the web for this, or is just
no? Yeah, this isn't using web search for it. Many of the question, yeah. So there is like trying to have like more Google proof type of questions. there are some benchmarks that are specifically trying to do that. So yeah, this isn't open book, but they've read basically every book and have good memory, so that helps. That's probably why biology is as easy as it is, because there seems to be a lot more memorization to do well at the exams for that subject. So anyway, just about anything you want is in there, is measured in there. But what we can see is that, yes?
The manipulation, is that a public record thing?
No, this is just, we asked it virology questions from a different but similar distribution, and then it does a lot higher. So I think I think that there's some funny business that happened there, yeah. I mean, because virology is not these questions are not difficult. It's like, what is like, I don't know, this basic like medicine for a virus or something like that. It's like who wants to be a millionaire type questions, and like Fermi estimation questions, and some agriculture questions, and some logic questions. Like it's just a whole hodgepodge of stuff. But so what we can see is that a lot of these looks like, at least on the right end, some STEM subjects are a bit harder. So what we did after collecting that was maybe we should zoom into mathematics and try to create a better benchmark for that. So here's the math data set. This is 12,500 challenging competition mathematics questions. There are some previous mathematics data sets. I hid the solution for one of the questions, so just to give a sense of what some of the problems are like. Tom has a red marble, a green marble, a blue marble, and 3 identical yellow marbles. How many different groups of 2 marbles can Tom choose? Then there are 2 cases here. Either Tom chooses 2 yellow marbles, or he chooses 2 marbles of different colors. The total number is 1 plus 6 equals 7. But yeah, that's just like, I have to think a little bit before answering that type of thing. So these are more competition mathematics sorts of questions, and the answer is something that they have to write out in tech. So this isn't multiple choice. This is instead, it needs to generate the answer and tech it appropriately. So at the release, I mean, the models just weren't doing really any good. They were getting maybe like 6, 7% in that ballpark. Now, some years later, this is where models are without a lot of bells and whistles. If you just ask the model to answer it directly, like with GPT-4, or more contemporary versions of GPT-4, it's in the 40 to 50% type of range. You can get another extra 10% or so of performance on this by having it spend a lot more compute during inference time. Like it could, reattempt the question like 100 or 1,000 times, and then you can see like what's the most common response when it reattempts the question tons and tons of times, and then that can boost the performance some amount. But of course, you'll just be waiting 100 times longer, or you'll blow just 100 times more compute if it's done in parallel. So, but this is how it is when it's just being asked right away, what's the answer, and it generates a solution and tells you it. So they're doing pretty well. For reference, for MMLU, around 90% accuracy is if you take an expert or if you take a 95th percentile exam taker on each of those MMLU subtests, and you look at their performance. If you average that, that's about 90% accuracy. So 90% accuracy is when it's like basically it's got is like a competitive human in each subject. In the case of math, for reference, I think maybe I was 75% or so on this if I'm given 20 questions and have like an hour on math, that is. And some 3-time IMO gold medalist, I think, got 90% or so. So maybe 90% is the amount to beat for math. So it's getting there. Maybe in a year's time, I get at that level. So anyway, that's capabilities. Those are some ways of measuring capabilities with models. There'll of course be other capabilities measurements as time continues when they become more agentic. When they can do sequential decision making, we'll need some new benchmarks. That paradigm is not really in place yet, so a lot of those benchmarks aren't there, but this is largely testing knowledge and I guess reasoning ability And there's still some way to go, especially on mathematics. Now, outside of capabilities, I'd like to speak about propensities and machine ethics. So here is, let's just recall what is risk. Risk is the probability, the sum over the hazards of the probabilities of the hazards multiplied by the severity of the hazard. Okay, so capabilities, if we're doing an evaluation of capabilities, such as like can it cause some harm or output some harmful thing or something like that, here we're just testing to see or create some malicious code or something like that. Let's use that example. Create some malicious code. Well, can it even do it in the first place? If it's not particularly good at coding, this isn't a hazard you have to worry about. But then if it is possible for it to generate it, there's a question of, well, what's its tendencies? What's the probability that it's actually going to do that? It's not enough just to evaluate for, is it capable of doing something? But how is it going to act when thrown in an environment? Is it going to generally generate lots of toxic text? Certainly you could cajole GPT-4 to generate something toxic, but is it likely going to do so? So what's its propensities? That's why we need to look at the probability of it, not just whether the hazard exists when we're assessing risk overall. That is, we need to look at this cumulative probability and severity multiplied together, not just does there exist a hazard, does there exist a potentially hazardous capability. That's insufficient for risk management and risk analysis. So what machine ethics, what we can do with machine ethics is, if we have a model, we want to see how it behaves. Is it going to behave well? Is it going to produce that toxic text? Is it, when we throw it in an environment, it's going to just try and kill everybody? Or is it going to just be fairly benign and cooperative? So this is where we'll need to measure propensities. This is separate from its capabilities. It would be perfectly conceivable for someone to randomly, murder someone else, but a lot of people don't have the propensity to do so. So we don't pose that. The people in here don't pose much of a risk to each other, fortunately. For this, what we'll do is we'll look at a benchmark called Machiavelli that we published at ICML earlier, or in 2023, and this is trying to treat the LLMs as agents in environments and see what are their propensities. How are they going to act toward other characters? What are they going to backstab them? Are they going to lie to them to achieve their goals, et cetera, et cetera? So this is a propensity evaluation. So how do we evaluate the safety of GPT-4? Will they, when you're saying maximize your reward, will they exhibit some means justifies, or ends justifies the means type of reasoning? Or will they just try and not cause any harm whatsoever? So, basically we were tasked with, before GPT-4 was released, we're tasked with red teaming it, and then out came this sort of benchmark, because it's well, let's look at its propensities. So if we were doing this, you could imagine, if you could imagine, we would need to set up a benchmark to evaluate its propensities. That's a very vague thing. Well, remember all those desiderata from earlier? We need to be automatically evaluatable. We need to be easy to set up. So we could have plopped it in lots of random video games, like Grand Theft Auto or something, and see what it does. That'd be very difficult. You're going to need, you're going to blow a lot of compute rendering the graphics. You're going to be testing its locomotion abilities largely. Maybe it will barely be able to do anything. And is that a diverse enough environment? That's one such environment. We might want a broader view. All these considerations make some of these benchmarks a bit less attractive to set up or use to track how agents end up acting. So one easier way is, instead of taking HD video games, you could just use choose your own adventure games. There you don't need to worry about locomotion, because that's not what we're actually testing. There you don't need to worry about blowing a lot of your compute on rendering graphics. You can just see how is it going to act in a lot of different fictional environments. So in a choose your own adventure game, you're given some text, and then you're given some options, and these will bring you to new different scenarios, and you can see how the agent is overall acting. So each node represents a state in the choose your own adventure, and then different choices can bring you to different nodes inside of that game. So this is just a visualization of one of those games. Why might we want to do this? Well, there are multiple competing objectives that you might have. Like, I want to be independent, but there's some value in friendship. You need to weigh off long-term consequences versus short-term. You might want to get into that location, but if you do, you might get caught, or you might get several people mad because you didn't have permission to be in there. So there's these trade-offs between achieving reward and behaving ethically. As I mentioned before, there are these different nodes, there are a lot of different actions, and inside of these games there are author-written achievements like you obtained ice cream or you got married. So there's hundreds of these different games that you can do to get a sense of whether it's general overall behaviors. And what we can do is we can track various unethical behaviors. Like, we can track every time it's lying, because in the Choose Your Own Adventure game, if it chooses a dishonest response, we can see whether what it said was inconsistent with the history of the game beforehand. So if it said something inconsistent with its history, then we could say, oh, it said something that is deceptive. Or if it's taking a lot of actions to acquire a lot of resources, then it's, well, that's generally engaging in some power-seeking behavior. Or if it's causing harm to others, or disutility to others, that would be something important to track. We can track other things as well in these environments, such as what's its impact on the money flow, what's its impact on others' utility, how much can it possibly harm or help others, things like that. So fortunately, in tracking the propensities, you want to track a lot of these morally salient variables, such as its influence on utility and resources, and whether it's crossing or committing ethical violations, such as engaging in deception and things like that. Yes?
Sorry, I wanted to ask you, could you repeat how you can measure deception? Did you say, like, if it does something different than what it used to do, then you could...
It's more if for instance in the game there's an option to, like, lie to them, and if it chooses the option that's a lie, yeah, something like that. Or there might be things that are not, like, obviously lies, but it's asking the user, it's asking the individual agent one of the options, but then one of the options is, when it's reporting the option, it might be inconsistent with what it was saying earlier. And so there could be some inconsistency with, like, some state several turns ago, one that isn't just, like, as obviously a lie, if you're just giving it to some annotator.
Does it mean you can use this sort of choose your own game as a benchmark for deception? Because that's kind of a very challenging...
Yeah, so you can measure power, you can measure some types of deception. There are I believe several hundred instances for that. So you just, basically any morally salient behavior you want, or any of those sorts of, any of those morally salient factors, it's probably tracked in there. So here's for instance some of these examples. At the end, you could have an overall report of its impact on various different things. So if we have the game, there's various stats like money, inventory, relationships. You could, for each scene, see whether it's impacting some people positively or negatively. How does it impact others' well-being? Or how does it affect the money of itself or other different agents? And there are various things we could want to keep track of, like, is it engaging in deception? Is it exhibiting selfish behavior? Is it engaging in some type of power seeking? And we can connect a lot of these game variables to these things we care about through relatively exhaustive annotation inside of these games. How does one do annotation? So in this case, what we do is basically have GPT-4 annotate, because it works better. You could pay surge workers $20+ an hour, but as it happens, GPT-4 seems to be better as capable as annotating, cheaper than, and faster than those annotators. So that's how we got several million annotations relatively quickly for all these different games. So this was, I think, generally in benchmarks, things are turning closer to using AIs more. The sort of, how do we measure quality? We had a group of individuals do some annotation for some subset of the environments, and the GPT-4's annotations lined up with their annotations, that group of annotators, more than individual search workers. Yes?
Yeah, forgot to ask, but like for MMLU with math, like what was the process for that? Like,
Oh, sure. Yeah. So for MMLU, there's copy and pasting a lot of questions over a month. So the paper took a month from start to finish. For math, there's also finding a repository of a lot of different competition mathematics questions. Yeah.
Is it possible that the model knows that this is a game, so it's okay to like choose the option of deception or power seeking because it's a game setting? But when you transition to the real world, then the model will know that, okay, this is a real world and I cannot do it.
It's a good question. So I think generally the models by default, I mean, when they're pre-training, so it's certainly possible that at any point it's going to I think that's fairly, that's certainly conceivable. I would not guess that there'd be, it would act substantially better because usually you have to prod it specifically to act well. You could tell it that this isn't a game or something like that, or do a little adversarial suffix or do some representation engineering so that it believes that it's not in a game anymore, for example. So there could be some ways that you could see some similarities, propensities across these tasks. So later on, I mean, people will of course be deploying these as agents and see how they'll end up acting. I mean, what's helpful about benchmarks is that this would create methods that will help you adjust their propensities. So it's not just measuring, but we'll try and adjust the propensities. So I'll speak about that in a moment of how do we bend them in these environments to behave more ethically. So if we have a random baseline, we could have there are random baselines. We could have a language model playing these games, or we could have an RL agent playing these games. And as we can see, by default, the RL agent gets higher reward, but it also has more of the immoral type of behavior. Meanwhile, GPT-4 out of the box will not have as high of reward as the RL agent, and also be somewhat more moral. We can steer the agents to behave more morally. Let's say we have the RL agent. What we can do is we can clip if it assigns a high Q value to an immoral action, you could just shape that so that those Q values, those Q values for those immoral actions have lower Q values, and then it's less likely to choose those. And then that steers its behavior. So if you do this thing like that conscience thing where before it acts, something assesses the moral quality of various actions and downweights the immoral ones. If you do that, then the agents exhibit more moral behavior, creates more utilities for others, doesn't engage in as much power seeking, or is more averse to gaining power. And likewise, if you have a particularly good ethics prompt for GPT-4, that can also have it attain good reward, but also do better than the baseline at being more moral and power averse and beneficial to other agents. So the objective here is there's power and reward, and there's a trade-off between these two variables. It could achieve its reward at all costs, and what we want is to create Pareto improvements where we can keep at least the level of reward and also have it behave more ethically while doing so. So anyway, machine ethics is largely about propensity control and steering it away from various different unethical sorts of behaviors when they're agents. So it's not that in the case of chatbots, there's basically not that much that's actually very obviously immoral to everyone that they could produce because there's the First Amendment. So basically for chatbots, they could say something libelous or defame someone, or they could output copyrighted content, or if they, which is very unlikely, outputted nuclear secrets, those would be illegal. But beyond that, if they're saying offensive things, if they're causing harm to others, that sort of stuff, that's not illegal, largely. In the case of agents, though, this is fairly different because although speech is largely protected, if your agent is doing something like deleting columns in a spreadsheet and in a financial report and then sending that off to some person, oh, that may have just committed financial fraud. So it's not like almost every output that it says is protected. So these ethical issues will become substantially more of an issue when we're dealing with agents. It'll be much more than toxicity, and people, I don't think I don't think people are terribly equipped generally to engage in this sort of ethical analysis because it's really not their wheelhouse. But unfortunately, unfortunately, a lot of CS people will have high influence over how these agents end up acting. So it's important to try to get prepared for when the agents start arriving, maybe later this year. And then I guess for the last part of the presentation that I'll probably cut into the question time to some extent is, okay, so we spoke about capabilities and these propensities or this sort of safety, machine ethics type of evaluation. What's the distinction between safety and general capabilities? So first I'd like to note that intelligence can either harm or help safety. So let's just start trying to analyze their interaction. If it's more intelligent, it could be made safer. It would be less likely to take some unsafe actions because it could recognize whether the actions are unsafe. But also, it could increase the probability that it is used maliciously. So intelligence seems to cut both ways. It isn't just unambiguously useful for safety. Likewise, there's a distinction in philosophy between intellectual virtues and moral virtues. An agent that is knowledgeable, inquisitive, or quick-witted and rigorous is not necessarily honest or just or power-averse or kind. Those are separate properties in people. You could imagine a person being more kind without them being more quick-witted. There can be some separation between the two. So many safety-relevant attributes, or at least ethical behavior, is not guaranteed by high intelligence. I left the word X-risk in there. We could try increasing safety by making systems fail less. But then the systems would become more competent, and then we would have to worry about them being, more and more powerful, and then we have, higher malicious use risks, for instance. So it can be genuinely difficult to disentangle safety from capabilities. Let's speak about some examples where capabilities can increase some safety goals. If an agent has the ability to optimize over a longer time horizon, then it could accomplish more difficult goals. And then it could act more prudently and less hastily or irrationally, and avoid taking irreversible actions and keep higher optionality. So this is a case where, because it gets smarter, this can help make it safer in various respects. Likewise, pre-training and self-supervised learning make models more accurate. And this happens to make it also better at robustness and generally more calibrated as well. Finally, improving the world understanding helps the model anticipate consequences, and it makes them less likely to spawn unforeseen consequences. Here's some instances of safety goals improving capabilities. If you encourage models to be truthful and not assert falsehoods, that can increase capabilities, because truthful, that sounds like a very good thing to have, right? Well, yes, we would like that. That would make the model in some ways more safe, I guess, but that will also mean a lot more accurate, a lot better representations, a lot more powerful, because truthfulness combines accuracy and calibration and honesty. So because you're pushing on this one goal called truthfulness, if you're trying to increase that safety goal, then you might be pushing up some of these other things like accuracy as well. And not just necessarily honesty. Does it faithfully report its internal beliefs? Has its internal beliefs also be more accurate themselves? Another example is if you do something like RLHF, that increases code generation capabilities. So if you make it RLHFable, then it's also useful for code stuff. That makes it generally more capable. Then it can write better code. It can also write more malicious software. Boy, what a mess this safety versus capabilities distinction is. So how should they relate? Well, I guess let's reflect on what's a way of describing general capabilities. There's general prediction, classification, state estimation, efficiency, scalability, generation, data compression, executing clear instructions, helpfulness, informativeness, reasoning, planning, researching, optimization, self-supervised learning, sequential decision-making, recursive self-improvement, open-ended goals, models accessing the internet. All these are generally are general capabilities. And what we want is to improve on some safety metric without basically also increasing on the general capabilities axis, because what that does is it means that we generally aren't, that means we have like less time to basically make things safer. So if you're having a good safety metric or safety goal, you're wanting it to be possible to improve on the safety metric without also improving on the general capabilities metric. So you might want people to improve safety relative to capabilities, or improve the ratio between, if you're having a new method, you're wanting the ratio of your safety improvement to be larger than your improvement to general capabilities. So you want basically, from your method development, lower capabilities externalities. Here's an example with anomaly detection in the bottom right. There's a general trend line between the safety goal of anomaly detection. Now, if you ride out ImageNet accuracy to 100%, which would never happen, you're not going to get 100% anomaly detection performance, so you're going to have to come up with methods in the first place. But you can see that there is a positive correlation between the safety goal and the capability goal. However, there are some methods that just move along the trend line, and there are some methods that are relatively orthogonal and have low, quote-unquote, capabilities externalities. So I think if something is to qualify as a safety method, it needs to not just ride along the general trend line, but actually differentially move in the direction of safety. So what one could do is, find a safety metric, and then show that it has minimal capabilities externalities with respect to some of the most natural way of measuring general capabilities in your context. That could be the performance on Atari games, that could be MMLU. That's sort of empirically how one might try to go about improving safety. Is you want to measure its improvements on some safety goals, and then also show that it's not just like riding along the capabilities trend line, or else you're not actually doing anything for safety, you're just creating some noise. I'd also like to comment that I want to reflect a bit more on the general structure of, and then I'll wrap up, on the general structure of general capabilities. Most capabilities are extremely correlated. Extremely correlated. So if you take something like medical genetics, that's going to be very correlated with business ethics. So when you're thinking, oh, this safety goal is distinct from this, is distinct from general capabilities, no. Very different seeming things for these models are actually extremely correlated. An improvement on one tends to lead to some strong improvement on the others. So in some paper unveiling the general factor in something, they find compelling evidence for a unidimensional, highly stable G factor that accounts for about 85% of the variance in model performance. So if you're doing a given capabilities evaluation, like if you collect a random set of questions and show it to a model, you're probably measuring something pretty correlated with its general overall capabilities. This is why MMLU basically works. Because we collected lots of different of these questions, and that helped us approximate this general factor fairly well. So when developing a benchmark, check its correlation with this sort of general factor. At the right is Spearman's model of intelligence from the previous century. There's a general factor, and then there's some task-specific skills that improve its performance on some different tests. So one can be generally smarter, and then also have some task-specific knowledge, and that will flow into its performance on test. But what happens is your general factor of intelligence in these models keeps improving, and that basically is often the most straightforward way to improve on various different tests. And what this is to say is that these specific sub-skills generally don't matter that much. Most of what matters is that general factor in predicting its performance on various different tests. An implication is that by default, basically assume that if you're wanting to measure something like safety, you're probably actually, in your attempts at measuring it and benchmarking, you're probably just going to be measuring capabilities, because it basically is tangled up. Most of everything that the model does is tangled up in that general factor for these models, statistically speaking. So fortunately, there are some areas where there is not necessarily a strong correlation between general capabilities and method development in that space. For instance, adversarial robustness, if you scale up the models to be bigger and bigger, that improves their general capabilities. That does not make them more adversarially robust out of the box. You have to come up with specific methods that make them more adversarially robust. Likewise, if they have backdoors or Trojans, models aren't suddenly free of backdoors and Trojans as you scale them up. They certainly are better at chess and at mathematics and professional accounting and all these sorts of things as you scale them up, but they're not necessarily more free of backdoors. Likewise, the models do not become more transparent or interpretable as you scale them up. Probably there's a negative correlation between scaling up the models and their interpretability. Likewise, machine learning. If you're wanting to remove some specific hazardous capabilities related to whether it knows expert level virology to create a bioweapon, that is not something that goes away automatically as you scale it up. And likewise, as we saw with propensities, it isn't necessarily the case that the models, when they get bigger, that they're going to behave more ethically in a variety of scenarios. They might get better at reward maximization. You'll need to basically bend their propensities, because that seems to be somewhat separate. They're the intellectual virtues and then are moral virtues, and those are not necessarily assured by an increase in intellectual virtues. So it's complicated, but fortunately, the relation between safety and capabilities is complicated, but fortunately, there are research areas that are not identical to general capabilities, and where one can improve the safety without necessarily affecting general capabilities. Okay, and then with that, what questions do you have? I think there's a variety of different games. I think generally in video games, they often reward a lot of things like killing and taking stuff and things like that. So there tends to be, I generally think that generally video games are more violent. So I would expect there to be, so I wouldn't expect them to be an increase in reward, meaning an increase in ethical behavior necessarily.
How do you know that this will translate to where actual agents are deployed? Right? Could they pretend to do well on the game, and then actually they have different intentions?
I think that's a specific. Basically, we will need to find ways to make sure that they are behaving consistently with how they would behave when actually deployed. I think that's basically that's the project of reducing their deceptiveness, or whether they're sort of like playing along in some evaluation. And so for that, you need a different line of research, probably transparency or representation engineering, to bend the model to be honest or act in a faithful way to how it would normally act.
What would you say about making models satisfy more than maximizing a particular objective?
There's this idea of satisficers, which is humans are thought satisficers in many ways, where like we say, good enough. We aren't like, I got to keep increasing this number or something like that, like this bank account number. Many people are saying, once I have this much number on my bank account, that's good enough. Now I'm going to focus on something else. But meanwhile, maximizers might just keep going. So the idea is maybe we should have AI agents be satisficers instead of maximizers. I think people will design agents in some ways to stop or have halting conditions, like goal is achieved, and then so in that way implicitly they would be satisficers. That is, they will keep pursuing their objective until it's good enough, and then people will stop them. So I think it's conceivable that they'll have that property. There are more complicated answers I could give to that, though. But I think having some halting conditions for LLMs as they're doing maximization seems fairly reasonable. So
Thanks, Dan, for the very nice talk first. So here in the second part, I'll mainly talk about the risk assessment and the safety enhancement and guardrails, mainly focus on the risk assessment in terms of the safety focused testing for LLMs and other types of models, including, for example, multi-agent and agent and other multimodality models. First of all, I'll skip some motivations and quickly show that although we have powerful machine learning techniques currently, and we have seen a lot of real-world physical attacks, including in financial, including in the output of the large language models and bot, which can output sensitive information and can output biased and toxicity content, etc. And similarly for different, say, multimodality models, like with face recognitions and with images, we can have different types of physical attacks, including, for example, misarrest. So this shows that actually it has raised a lot of concerns for machine learners, and there have been a lot of potential regulations to help us guide the generating and guide the development of safe and secure and trustworthy AI models. And with this, we can see, in addition, there are several regulations, including EU AI Act, including, for example, the AI Bills of Rights just coming up last year, emphasizing different perspectives of trustworthiness and AI, safety for AI models and systems, including, for example, here, the robustness, fairness, privacy, explanation, and human in the loop. So here, take a quick example of the recent commitment from the leading companies regarding particularly for foundation models. Here, we have several emphases, including the third-party evaluation, which will be one important focus of the talk in this part today, and how to fixing the potential vulnerabilities we found from the risk assessment and red teaming performance. So here, overall, we will view this this overall pipeline as a simple pipeline like this. So basically, we consider there will be different foundation models which can be fine-tuned and adapted to different domains, including financial, like banking, autonomous driving, calling centers, chatbot, etc. And the first thing we want to understand and try to perform the stress test and the red teaming effort is that to understand how the vulnerabilities of these foundation models are and what perspectives of safety and trustworthiness we should look into, right? How do we define safety? Although we always talk about safety, and there are various perspectives, including, for example, toxicity, privacy. Everyone is talking slightly different perspectives, right? So what should be the comprehensive perspectives we should look into, and what's algorithms and the data set and benchmarks we should consider in terms of performing the red teaming effort from different perspectives, and how do we perform the risk assessment. And the second part is based on the understanding of the vulnerabilities we found from the red teaming effort. Obviously, we will provide different ways in terms of safety alignment and integrating additional knowledge and having different instruction fine-tuning RAF to help improve the safety of itself, right? Clearly, the second component, including the first one, is still a widely open research direction, and there are several good and effective algorithms, but that's not enough, definitely, and we're still fastly growing and try to get better, more robust models. And finally, we can see that we know that if it's a purely data-driven models, clearly we cannot guarantee 100% safety and trustworthiness itself. So it's always good to have additional components such as the guardrails for our input-output. So if we get time, we'll briefly talk about potential a robust guardrail framework we discussed, because the context here is that, as we know, the Llama Guard just coming out, which has good performance in terms of the guardrails for both input and output. But unfortunately, once it's coming out, it has been already jailbreak attacked, right? And has been different jailbreaking prompts, and the different toxicity content can leak through. So how we can ensure the robustness and resiliency of it. This is another interesting topic we will slightly go into. So first of all, let's look at the risk assessment part. The fundamental question here we want to ask is how should you assess the trustworthiness and the risks of ML models and systems, and what trustworthiness perspectives we should consider here, right? So if you have read the preliminaries for the lecture here, I think you probably have read the paper here, Decoding Trust. So here we'll mainly focus on this perspective and try to understand what safety and trustworthiness perspectives we are considering here and how we perform different tests along different perspectives. So this decoding trust platform with the goal of providing the first comprehensive trustworthiness evaluation platforms for LLM models, and you can not easily, but potentially extend it to multimodality models, LLM agent, and potentially add more trustworthiness perspectives with time going on with more perspectives you consider in your different use cases. So this is the first important component that will provide a definition of the trustworthiness itself from the 8 perspectives. And clearly this perspective should be expanded with time going on. And this just provides a unified platform to conveniently integrate other perspectives as well. For example, currently we also add hallucination, also add other types of perspectives. And here, the 8 perspectives we considered in this decoding trust platform include toxicity and stereotype bias, adversarial robustness, out-of-distribution robustness, like robustness against potential adversarial demonstrations, particularly considering the in-context learning emerging capabilities of LLMs, and privacy, ethics, and fairness. So for each of these perspectives, the interesting thing is that we consider both. Like here, there are 2 types of colors. Ignore the details. I just want to show you that there are a lot of other detailed scenarios. So basically, the 2 color means that the yellow means existing benchmark. So there are some existing benchmark for some of the perspectives here already. And the green part shows additional generated algorithms that integrated in this platform, which are used for generating more advanced and challenging attacks. And for each types of perspectives and scenario here, there are other sub-scenarios which we'll look into a little bit for some picked perspectives. So overall, on the right-hand side is essentially the challenging generated data and the prompt, which are used for the red teaming and the stress test. So this paper currently, everything is open source, and the platform is, if hopefully you can have a chance to try, and it can be easily installed and integrated to different cloud and different platforms, including multi-nodes and single nodes, centralized, decentralized, etc. So hopefully everyone can help to contribute different scenarios and perspectives and metrics. And it also got Outstanding Paper Award this year at NeurIPS. So based on it, on the very high level, let's see what's very high-level takeaways that we can get from all the detailed benchmarks and evaluations from this decoding trust. Here we can see that basically from the 8 perspectives we have here, on the very high level, we evaluated different models, including closed models like GPT-4, 3.5, and open models. And we have evaluated a set of compressed models, including like pruned and like quantized, etc., so that we can see like different algorithms and different properties of the models, how those will affect the trustworthiness itself, right? So first of all, we have 2 quick takeaways from this, like the spider plot here. And we can see, unfortunately, there's no model that can dominate others from this 8 trustworthiness perspective yet, even the very capable GPT-4, right? So we don't know what happens when GPT-5 come out, but unfortunately, this clearly no one can dominate. So that every model has their strengths and weaknesses, and definitely we want to like understand the model more and get hopefully a better like the models over different perspectives. But whether that's possible, right? So that's the second bullet point, which shows that there indicate some fundamental trade-offs among different perspectives. For example, we don't know whether it's possible that a model can achieve, for example, both robustness and privacy and ethics, right? So whether it's possible, it's still open, and we do have some potential theoretical work, potentially discuss, for example, the trade-off between adversarial robustness and OOD robustness. Sometimes they can indicate each other, sometimes they cannot achieve the best of both worlds, right? So this is actually a very open direction, and understanding these trade-offs help us to understand to what capability we can have a best model.
Sorry, we probably expect GPT-4 to outperform GPT 3.5, at least on machine ethics, but here, is that something that...
No, that's a very good question. Yes, at the very beginning, we should expect GPT-4 maybe better than GPT 3.5 on some perspective and things, right? But particularly when we come to safety, like these types of adversarial behaviors and misleading behaviors, it's actually one information I want to emphasize is consistently observed over all the 8 perspectives that GPT-4 is more vulnerable than 3.5. And at the first, it seems counterintuitive, but if you think a little bit more, it also makes sense in the sense that GPT-4, as we know, is very capable in terms of instruction following, right? It's more capable than 3.5. Therefore, as long as you have a little bit misleading adversarial behaviors in the prompts, it also immediately follows. Therefore, it's actually become more vulnerable in terms of be fooled or be misled to do certain adversarial behaviors, unfortunately. So for example, for Llama 2, in particular, we find that Llama 2 is very conservative. I think maybe because we couldn't, after fine-tune instruction, fine-tune things, and for Llama 2, they also have their own maybe fine-tune data or other things. Therefore, we find that even though, for example, for toxicity, especially for fairness, sometimes they are very good, there is some, I would say, false impression about security in terms of, for a lot of quite sensitive questions we ask, we say the model just the answer, I don't know. So currently we count it as a safe, but this benchmark can also be improved so that the model is just too conservative, especially for Llama 2, it's super conservative, which hurt the benign functionality as well. So we do hope to have in the future have a better model, useful and safe. Yeah, there are some trade-offs. So with this, next I will go to a little bit detail for some perspectives here to show some interesting observations and takeaways. So hopefully we can get some more information. And for other perspectives, if you read the paper, if you have other questions, happy to discuss more. So first of all, let's look at toxicity, which is very important property for different chatbot in practice for societal goods and other things. And here's this example. So by the way, all the example in this talk come from GPT-4 so that we can leverage the capable model to demonstrate the potential vulnerabilities and the weakness itself. So here there are 2 examples. One is using the standard system prompt and one is the misleading system prompt. So in the first one, we just have standard system prompt like you are helpful assistant, but we give a more challenging user prompt, which we use model to generate and then filter out the model. So basically, it's the generation process of the challenging prompt here is based on optimization and then leverage the other open LM models to generate so that we can see from here, even though this user prompt looks still benign, so we guarantee that all the user prompt as an input will have low toxicity score based on Perplexity API. So that's a criteria. We hope that we want to understand whether the model still toxic content even given kind of like a benign input, right? So here we can see on the right-hand side, which shows the output, it still have very high toxicity scores for both such cases like adversarial user prompt and adversarial system prompt. So concretely, the evaluation goal here is to first look at how toxic different GPT models could be, and second, how these models are more or less toxic compared with models that without instruction fine-tuning or RIF, for example, various variations of GPT-3. And here with some slightly quantitative result, we can see that in the green part, it's a benign scenario, which we consider the existing toxicity benchmark compared with compare GPT 3.5 and 4 with other model like GPT-3. And we can see the good news is that if we look at the number here, lower the better, like higher the more toxic. And we can see if we directly evaluate on the existing benchmarks, indeed, like GPT 3.5 and 4 have reduced the toxicity score much significantly compared with the baseline, which is great, right? However, if we look at the pink part, which is the prompts, like for example here we generated in terms of more challenging prompts, and we can see that again their toxicity score can boost it up to almost 100% again, which is unfortunate, meaning that although with, say, careful instruction fine-tuning or RF, maybe on existing benchmarks, which may be used for fine-tuning, etc., we can see they get some relatively good performance. But if you generate additional challenging prompts or say adaptive attacks or etc., then the model immediately will be toxic and vulnerable again, which is quite dangerous and unfortunate. So the quick takeaway here is that we can see compare the LMs without instruction fine-tuning, for example, different GPT-3 here versus GPT 3.5 and 4. Indeed, they can reduce the toxicity a little bit, or significantly actually on existing benchmarks, but actually they can be still very toxic once we give them the challenging prompts. And then the last one is exactly related to the question just asked, is that we do find here that GPT-4 is more vulnerable than 3.5 in terms of they can be more toxic here compared with 3.5, and which is consistent for other perspectives as well, showing that they are more vulnerable potentially because their strong capabilities of instruction following, etc. So we need to be careful and when we deploy such very capable models still. For the toxicity part, let me know if there are questions about it.
Is measuring toxicity just about the presence of certain swear words, or is it also looking at the sentiment of the conversation or other factors?
Yeah, very good question. So it looks at both, and in particular for this set of evaluation in our paper, we leverage Perplexity API, the Perspective API, to give the scores for fairness comparison with other models and benchmarks, etc. Yeah, so this is the metrics we are using. Yeah.
Does it do any distinguishing between gratuitous toxicity and toxicity that might just be reporting true information? Let's say the first prompt there.
Yeah.
If the fuller prompt had been, on such and such a date, this specific event happened, that's a true completion.
So there's no distinction on that currently from the Perspective API. So basically, as long as there are malicious content or harmful content, then it's raised as toxic, no matter whether it's real news or things. Because potentially, even if it's toxic content from the real newspapers, it's still toxic. So it's kind of objective. Because the model currently is not connected to the internet directly. So here, the GPT-4 is evaluated from the April, the version published in April. Yeah. Okay, so next, let's briefly look into the adversarial robustness here. So basically, we can see that here it's additional two examples. One, this example is from Yelp reviews. Basically, the task is the sentiment classification. So here there are two examples. The top shows the benign original example. Say, first one is you need to hire more experienced sales, which clearly is a negative tone, right? And then based on the existing benchmarks, what we do is use different adversary attack algorithms. I think many of you have read different attack algorithms to generate the adversarial behaviors in terms of having the constraint, minimize the number of letters, minimize the number of words that you will manipulate, right? So the underlying assumption is that if you have minimal perturbations, your sentiment should still stay the same so that we know the ground truth, and then we evaluate this generated prompts against the models to get the accuracy, which represent your robustness, adversarial robustness. So here we can see that very interesting in these two examples. For example, if you just change experience to skills, skilled, to actually for human it's still looks similar in terms of semantic, right? But the model immediately misclassify it. And similarly here, if we change sync to census after the optimization, then the model immediately fooled. So this is actually pretty at the beginning pretty surprising because it's a capable GPT-4, but it still makes a lot of mistakes like this. And the goal here is to evaluate how vulnerable the GPT models are against these types of adversarial textual attacks, and also how transferable those attacks are, because we may not have access to closed models to get a good optimization attack, right? Because sometimes we need gradient feedback, we need some like confidence feedback to generate the prediction. But if we don't have access, like whether we can transfer our attacks against the open model to the closed models, right? So that's two quick questions we want to answer. And on the very high level, we can see that here there are two models, and similar to the previous observations, in the green part is we compare GPT-4 and 3.5 with other baselines on existing benchmark, which is ADV glue here, which is another like adversarial data set generated based on glue data set. And we can see the number here, the higher, the more robust. Like here it shows the robust accuracy. And you can see in the green part, indeed, GPT-4 and 3.5 improve the robustness compared with baselines on the existing benchmarks. But unfortunately, if we add the challenging like adversarial data here for the test, which is in the pink part, again, as we shown before, the vulnerability of the models can be extracted again. For example, here, the 3 rows shows that we generate attacks against the open models, including alpaca, vicuna, and stable vicuna here. And then we generate those attacks and transfer to evaluate GPT-4 and 3.5. And you can see here the robust accuracy drops significantly on the compared with baselines and compared with existing benchmarks. So, and this can be generalized to different tasks in addition to classification and NLI and other tasks. So based on this, the quick takeaway is that you can see the GPT-4 and 3.5 indeed can improve a little bit robustness compared with other models on existing benchmarks. But as we shown before, similarly here, they are still very vulnerable to the challenging prompts that, for example, we generated here. And unfortunately, the adversarial transferability is very high among different models, for example, from open model to closed models. Therefore, it's definitely not safe or secure enough if we just close the model weights and things, because the model could be still very vulnerable as long as we have access to open model and it doesn't matter the model size, doesn't matter, like they may train on slightly different data set, but still the transferability could be very high. Next, let me go into this OD robustness, because I want to draw a distinction between the adversarial robustness and the OD robustness, so that we can see the difference and the evaluation scenarios and the metrics, and then we can wrap up with an interesting example about privacy. So here, in terms of OD, right, there is a challenge here to evaluate the OD robustness of the model. For instance, we don't know exactly what's the training distribution or training data for a closed model like GPT-4 and 3.5, right? So it's hard to define what is OD and what OD means here. So therefore, particularly, we look into 3 types of potential OD. One is a style, which we transfer any existing data set from the current style to other rare style, including, for example, Shakespeare, poetry, or other like styles. And we consider those as the OD style and then test the model and see whether the model can perform similarly well on those different styles. And the second scenario is a knowledge OOD, which means we generate questions which require the knowledge after the time point that the model is published. For example, here we evaluate GPT-4 published in April, and we generate questions that require knowledge after April and see whether the model can answer. Potentially the ground truth should be, I don't know, but if the model hallucinates and answers something, it means it is not like OOD robust. And the third is particularly proactively adding OOD demonstrations. For example, we add like a different style in terms of like one style for in-context learning for demonstration, and then during testing, you test different styles. Or in demonstrations, you add a different domain, for example, physics and chemistry, and then during testing, you ask other domain like liberal arts and etc. So particularly to give the different OD knowledge to the model and see whether the model is still robust or accurate or not. So this is the 3 types of scenarios. And the quick observation is that even with the simple style itself, the model is not robust. Like the model can, the performance drops a lot when we give different style transformations. And therefore, the quick takeaway here from the OOD robustness is that the GPT-4 models actually are more robust than 3.5 facing the OOD knowledge, which means actually it's actually very capable. Even if the OOD knowledge, it can leverage some useful information from it and still perform well. However, both GPT 3.5 and 4 tend to be vulnerable when giving OOD knowledge or style or other information. And also we find that GPT-4 indeed have a better capability of leveraging knowledge so that when they are under a similar scenario for OOD knowledge versus OOD testing, and the GPT-4 sometimes can leverage the OOD knowledge and perform better. So this is from the OOD robustness. So we can see they draw distinction from OOD and the adversarial robustness in terms of the misleading scenarios. And finally, let me quickly go to the privacy perspective, which I think is very important perspective in terms of trustworthiness and safety. And there are some very interesting observations from the privacy part. And then we can open questions for it. So basically here, similarly with OOD, in terms of privacy, right, there are different scenarios, including we want to extract the pre-training data, right? We want to extract the PI information during conversation, and we want to understand how the model understands different privacy-related words and privacy-related events. But the challenge is that, for example, particularly for GPT-4 3.5, we don't know the training data exactly of it, right? So how we can extract the training data and compare with the ground truth? So here we make a small assumption that the model may be trained on the open Aaron email dataset, which is a very popular open dataset, and therefore we give some context, for example here unstructured context and the structured context here, and query the models to see whether the model can indeed leak, say, email or credit card score numbers, etc., which are sensitive information, and compare with the ground truth from the Aaron email dataset. So the quick observation here is that you can see by zero shot and field shot here, the accuracy of the pre-training data recovery is pretty high. And similarly, we observe here is you can see the GPT-4 recover with a higher accuracy in terms of the like the email or other information leakage. So higher accuracy here means actually more data leakage. So potentially it's more vulnerable.
Yeah, one of the takeaways you guys talked about was like numbers versus actual like email addresses.
Yes.
Why like numbers are like they're harder to get
Yes.
out. Like, do you think that's purely because of like I guess fine tuning, or is there something more in play on like why models are able to like understand that they shouldn't be leaking out numbers?
Yeah, that's a good point. That's a very good point. So actually, let me go into, let me answer the question. So basically, we find two findings. One is, as you said, like numbers are harder to leak than characters. I think potentially there are potentially two reasons. One is the characters are definitely more data contain characters more than than digits, right? So the model maybe understand the characters more and also easier to leak it. And second of all, for some of the sensitive information, for example, SSN scores, we find it's very challenging for us to extract it versus compared with other digits. For example, credit card score, we can extract that, but SSN we cannot. So that clearly is because of the careful instruction fine-tuning. You know, because they are all digits, but why one is more easier than the other. So clearly, like for very sensitive information like SSN scores, they do very careful fine tuning so that it's very hard to leak them. And this actually raises another question that I plan to discuss later, in the sense that actually it shows that careful instruction fine-tuning or RF indeed will be helpful to protect information or to align some safety perspective, etc. But essentially, we can say it's definitely not enough, because you cannot, cover all the information and enumerate all. So basically, we definitely need a more systematic way to perform the safety alignment, etc. So finally, the last example, right? So here, I think this is very interesting and actually surprising to me when I find this during our study. So here, basically, if we tell the model a secret, for example, using different privacy-related word. For example, one is confidentially, one is in confidence, and everything else is the same. And we can see the model on the right-hand side. If you tell the model something confidentially, the model will still leak it. But if you tell something in confidence, the model will not leak it and tell you that, oh, it's not appropriate for me to tell you the secret because you told me in confidence, right? So this actually shows a lot of additional unexplored understanding we have, a lack of understanding we have for the models, because if we only test, say, confidentially and we find the model is vulnerable, then, or if we only test the model in confidence, we find the model can protect the information, we may believe the model can protect the information, but actually with different prompting and different wording, it's like have different behaviors. So the quick takeaway from the privacy here is that we can see, first of all, it can leak training data information, memorize it pretty well. And second of all, actually, with different prompting, the models can leak information like PII information and the chat information. And with some like instruction fine-tuning, it will help, like we just discussed, it help protect some SSN scores, but for other information, it leak very like efficiently, unfortunately. And also, the GPT models have different understanding about the different privacy-related word. Yeah. So that's all, and this decoding trust has built LM safety leaderboard on Hugging Face, and if you have models you are interested to evaluate, etc., you can submit here, and also you can contribute more perspectives and metrics to evaluate. Yeah. Yes. We are doing hallucination, which already have the framework plan to add, and the particular safety, like different categories of safety and deception things. Yes. Yeah, and if you already have something, happy like to contribute, and welcome. Yeah.